Hello, everyone. Thank you for joining today for the Grow Your Knowledge webinar. The webinar today is on heat pump installations for large non-domestic buildings around our new AM17 launch. Today I'm joined by some of the authors of this new AM. And just a reminder to everyone that this Grow Your Knowledge webinar, you will receive an email tomorrow, which will have a link to the recording. And also it will include your certificate of attendance. Please do use your question function in your webinar dashboard to ask questions throughout, and the panel will get round to answering them at the end in the Q&A session. So I won't delay any further, and I'll pass on now to Michael Edwards, one of the AM17 authors. Thank you, Michael.
Thank you, Lucy. Lovely to be here. Yeah, it's great to be here to present this webinar on Cibse Applications Manual 17, heat pump installations for large non-domestic buildings. As Lucy said, my name is Mike Edwards. I was the project director of the authoring and review team here at Arup, and we're really happy to be here to talk to you on this exciting launch day. So I'm joined today by two of our authoring team, Iona Norton and Alec Tyson. On the next slide, we'll see the agenda for the day. I'm going to give you a brief introduction into AM17, what its purpose is, briefly what it talks about and how you might use it as a reader and a designer. Iona's then going to talk a little bit about the application and design considerations for different building types. As you can imagine, non-domestic buildings covers a lot of different building types. So within the document, we've written about how you might apply a heat pump design and what kind of considerations different types of buildings have. So Iona's going to take you through that. Obviously, we're not going to talk about the whole document, but it'll give you a flavour of how you might use it and the kind of resources it has. And then finally, Alec will showcase some of the case studies that we've included within the document. These are really important as they provide real life examples of heat pump design challenges and solutions. They highlight some of the things that you will see in real applications and show some of the solutions that you can use to really optimise heat pumps. So, worth saying that this work builds on AM16, which is the heat pump installations for multi-unit residential buildings, so large residential buildings. So we delivered this last year with a similar authoring team to Cibse, and this document really builds on that work, and you know it shows the importance of heat pumps that BEIS and Cibse have commissioned a follow-up to this to cover remaining large building types to talk about the installations. I'm going to show you a brief slide that talks about the authoring team, the peer group, the peer review team, and the team at Cibse. So, as I said, most of the authoring team are here today. Josh Bird and Ilaria are not here today, but they are here in spirit, I'm sure, possibly even listening. I'd like to thank the peer review team who really helped us, and challenged us on some of the aspects of this document. And the steering group team were also fantastic, made up a lot of different industry stakeholders. We had clients, we had contractors, we had people from other heat pump federations and other designers who really, reviewed our work and made sure that it was relevant and useful to you as Cibse members and other people within the industry. So it's been a real pleasure working closely with the team at Cibse, with Eileen, Howell and Colin, and our editor Ken Butcher. So a big thank you to all of those people. Worth noting that because this is a government funded document, this is actually free to download. So if you go to the Cibse Knowledge Portal site and find AM17, you can download the PDF version of this for free using the voucher there. So this is intended to be a resource that's freely available to all. We want it to be as well used as possible, as do Cibse and BEIS. So that is how you access it. So in simple terms, why have we written AM17? So the document is intended to support successful delivery of heat pumps. Iona is going to cover some of the measures of success which we've stated within the document, but I think it's fair to say that decarbonising heat is a particularly important goal, particular strategic goal here in the UK. We have legally binding targets to achieve net zero greenhouse gas emissions by 2050. Achieving this will require virtually all heating buildings to be decarbonised and heating industry to reduce close to zero carbon emissions. I think you're probably aware that heat from buildings and transport emissions are sort of the two main areas where we've made limited progress in the UK in decarbonisation terms in recent years. So it's really important we do more, and it's widely acknowledged that heat pumps are a key part of that. To do that, we need delivery at scale. So this document covers a wide variety of building types, giving guidance on what key issues are to be considered for different needs. Heat pumps can and will be widely applicable, and scale is super important. Making sure we get this right is very important. So the UK government's ambition is that we move from something like 35,000 heat pump installs a year to around 600,000 in quite a short space of time. And I think it's really important this is done well. Clients, operators, consumers need to have confidence they're getting high quality installations that deliver for them. So as an industry, we really need to avoid poorly designed or installed heat pumps that dent people's confidence in them as a technology. So hopefully this document will support that aim. And I think while this guidance is probably useful to all involved in the industry, it is principally aimed at building services engineers, and therefore it does assume a base level of technical understanding around systems. The document isn't a detailed guide on heat pumps, compressors, evaporators, that sort of technology. It is an applications manual, so it's all about how you apply this technology to buildings. In terms of the scope, we have, after discussion with BEIS, with our steering group team, we define large installations as those over 45 kilowatts of thermal energy. The document doesn't talk in detail about the choice of heating system. It assumes that a heat pump is a chosen technology already. Obviously, within that, there are lots of different types of heat pumps, different types of refrigerant, different types of applications, ground source, air source, etc. We cover all of those things. But it's not intended to be a should you use a boiler or a heat pump type guide. It assumes that's been chosen already. It covers non-domestic buildings and a wide variety of non-domestic buildings. We'll talk about some of that in Iona's section and in some of Alex's case studies. And it covers existing and new buildings. So obviously, it's very important that most of the buildings that exist in 2050 already exist today. So decarbonising them is just as important as your projects where you're getting heat pumps into new buildings. So we cover some of the specific challenges around retrofitting heat pumps, decarbonising existing buildings, and focusing on bringing loads down. So that's what the document is for, and that's what it covers. My final slide before I hand over to Iona is just to highlight a similar diagram that we had in AM16. You'll find this within one of the first few pages of the document. What we wanted to do is make sure we signposted to other useful documentation around heat pumps and associated challenges. So on the left-hand column, you'll see other resources. So this highlights lots of other guidance which you can look at around heat pumps to help you where our document doesn't cover those things in detail. The middle section kind of navigates you through the design process and installation process as we see it, highlighting the sort of process you should probably go through. And then on the right, using the application manual column effectively relates this process to the different chapters we have. So for instance, if you were looking at monitoring, you would look at chapter 8 at the bottom now. It's very hard for me to see that. But this guidance really is a quick reference to allow you to jump to sections that's most applicable. I'm sure if you're anything like us, you're not going to spend all your time reading a guide from cover to cover. So this allows you to skip to the sections which are most relevant to your role and your application around heat pumps. So very pleased to introduce this applications manual. I'm about to hand over to Iona now, but I'll be around for questions later. So over to you, Iona.
Hi everyone, and thanks Mike for the introduction. I'm Iona, one of the main authors of the document and also a mechanical engineer at Arup. So I think I wanted to talk about some of the main sections of the document, and in particular, some of the things where, in my experience, designers have had particular questions or, have had particular difficulty in deciding how they should choose or design a particular element of a heat pump system. So the diagram that Mike showed before kind of showed the structure of the document, and we really tried to make sure that it walks the reader through how you might make some of the key design decisions. And one of the key design stages when you're looking at a heat pump system is to really understand the loads of your building and any requirements for those loads. And this is kind of, the document is supposed to help you design a heat pump system for a new build, retrofit, or many different kinds of commercial or non-domestic buildings. So it could be a hospital or a data center or a commercial office. And the main way that a heat pump system will respond to those is by really understanding the difference in the load characteristics of those different buildings. So one of the early sections is, what are your load types? How can you reduce those loads following the kind of heating and cooling hierarchy, and like reduce demands as much as possible? And then once you have done that, what are those loads? And not just what are the peak loads, but also how do the loads vary annually? What is the daily profile? What is the coincident heating and cooling load? Are there any restrictions on how much resilience is required depending on your building type? Are there specific emitters that you need, and do they have specific distribution temperatures that are required? Or for a retrofit application, are you limited in your distribution temperatures by existing pipework? So we kind of have some diagrams like this throughout the document to help you look at what steps you need to take. And on this slide, you can see a kind of combination of information that you might collect for your building to understand your loads. And this is something that's particularly important with a heat pump system, where you might be trying to maximize heat sharing. You might have multi-use or multi-load development with quite a lot of different considerations. So it's not enough to just understand your peak heating, cooling, and domestic hot water load. It's also, do you have resilience requirements on heating or cooling or domestic hot water? Are you limited in these temperatures? And how do those loads vary throughout different periods of the year or day? And how, therefore, might you size your heat pumps or thermal storage to deal with that? So that's kind of the first section, and something that's really important and that is often kind of underestimated because it can take quite a lot of work. So once we've kind of gone through the section of what are your loads and how do you define them, we have a section about what technology you're going to choose to meet those loads. And as Mike discussed, like, we've kind of made the assumption that by reading this document, you've made the decision to use a heat pump, but there are a lot of different kinds of heat pumps, and you might use heat pumps in conjunction with another kind of heat pump or with another solution as well, depending on what restrictions you might have for your development. So we have a section that discusses different heat sources, different refrigerants, different performance characteristics, and why you might make the decision based on the loads that you've defined to use a particular technology. So once you've defined your loads, selected your technology, you then want to size the different bits of kit. And I particularly wanted to talk about one bit which I get a lot of questions about, and what can be quite challenging is early in the design stage, designers often struggle to work out how much space might need to be allowed for air source heat pumps in particular, because air source heat pumps require a certain amount of quite high in demand outdoor roof or outdoor space. So to try and give designers a rule of thumb that wasn't really present in other documentation, we contacted a lot of manufacturers and tried to produce some graphs that show, for different types of air source heat pumps, what the dimensions might be for different heating and cooling capacities, and what clearance is required for airflow and access and maintenance. So hopefully this gives designers a kind of good rule of thumb for space planning early in the design stage. Another thing that is often a sizing and spatial consideration is the use of thermal storage. So thermal storage for heat pump systems is often required for a multitude of different reasons. So you might employ thermal storage to peak lock your loads. You might use it to increase your minimum system water content. You might use it to address resilience and defrost cycles in air source heat pumps. You might use it to maximize heat sharing where you've got heating and cooling loads, or you might use it to give yourself some demand side flexibility. So being able to charge your heat pump and charge your thermal store using your heat pumps in a period of low carbon grid intensity, or when electricity prices are lower. So there's a lot of different reasons why you might use thermal storage, and there's a lot of and depending on how you wish to use the thermal storage and the purpose of it, you'll size it accordingly. So we've kind of gone through the different reasons you might employ it, how you will size it. And this is something that often needs to be brought into the design early because it can be quite large and particularly tall, where you're looking at maximizing the efficiency of the thermal storage and stratification. So this was something I kind of wanted to highlight, and which we've given a bit of emphasis to in the document, because it is specific to heat pump installations in particular. So I've kind of briefly covered some of the main steps. So we've looked at what are your loads, how do you reduce them, and how do you define them? Then what technology are you going to use? Then how do you size that technology? And then the document has some sections on efficiency and bringing together your building schematic and how are you going to operate it most efficiently. So I wanted to talk a little bit about the efficiency of heat pumps. So the efficiency of a heat pump is characterized by something called the COP or EER, so the coefficient of performance or the energy efficiency ratio, which is basically the ratio of the useful heating and cooling output to the input electrical energy. And that efficiency depends on lots of things, and the specific technology of the compressors and the refrigerant used, but it also is really dependent on the temperatures at which you're distributing and the temperatures of your heat source. Now, your manufacturer will provide the EER or COP for each unit. However, it's worth noting that this COP will vary depending on your source temperature. So if you're using a heat source that changes in temperature, your COP or EER will vary throughout the year. And it's important sometimes to request that information where manufacturers might not provide it. In particular, you don't just want to know the COP at a particular point in time when you might have your peak load. You want to understand how it varies across the year and what the kind of average COP or efficiency is. So often manufacturers use something called the seasonal coefficient of performance or seasonal energy efficiency. The value that is reported on data sheets can often be calculated according to certain standards, which assume a weather profile, a part load and load performance profile, and certain distribution temperatures. These might be completely different for your application in your building, which might have a different climate, a different profile, and different distribution temperatures. So the values shown on data sheets in this instance might be much less accurate than a seasonal energy efficiency ratio that you've calculated yourself using COPs for different source temperatures that you know for your distribution temperatures and weighting them according to your load profile. We've included in the document what we've called a datasheet decode, which is something that we hope designers will be able to use to understand what are the different things that manufacturers report on their data sheets, what is useful, where might you need to ask for more information, and what do some of these things mean. And this is something we've seen has been quite useful, in which we also included in AM16, the residential heat pump guide. So moving on from general concepts of efficiency, we also look at, how might the system as a whole operate? And while this isn't a heating and cooling network optimization guide, it's considering heat pumps themselves, it is really important to think about how heat pumps operate as part of the wider system. So, and something that is sometimes underestimated is the importance of a designer understanding how the system ought to work. So when should these heat pumps turn on and off? How should they interact with other aspects of the system or other heat sources? When are they most efficient? How should they be prioritized? How should they be staged? And it's not enough to just leave this to the designer of the BMS. The designer of this system really should understand what are the trigger points. When should this turn on? When should it turn off? How do we know how much heat is stored at any one time in the thermal store? When should it be discharged? How much heat is being transferred to and from a ground system? And so we kind of give some examples of how you might write a controls narrative, which can then be translated into a more rigorous BMS system. And finally, so I've skimmed over what is quite a comprehensive document and has quite a lot of sections. But I think the aspects that I've summarized so far, so what are the loads, what technology you're going to use, how do you size it, how do you optimize the system, are followed by sections on installation, commissioning, and end of life. I wanted to highlight, however, that while we're going through this process, what are we really trying to achieve? We're trying to achieve a successful heat pump installation, which we've defined as something that reliably delivers the heating and cooling loads to the building occupants and clients, that's easy to use and easy to maintain, low energy use in operation, safe to operate, future-proofed and resilient, cost-effective from a whole life, capital, operational, maintenance, replacement, cost perspective, and also carbon efficient from a whole life perspective. And so some of these things can have some contradictions, and you might need to make some trade-offs or compromises. For example, it can be commonly thought that installing a heat pump is always a good thing because they're much more efficient. However, the embodied carbon impact of a heat pump is not insignificant. And so where possible, the installed capacity of your heat pump should be reduced, and perhaps you can use thermal storage, or in some cases direct electric, in order to reduce the installed capacity, maybe at the expense of operational carbon, but with an overall embodied carbon and whole life carbon positive outcome. So I think it's worth thinking at the time, while you're making all the decisions along the design process, how does this impact on these measures of success, which might vary in importance depending on your project. So I hope I've given a good overview of what we've tried to achieve in the document and some of the important sections. I'm going to hand over to Alec now, who's going to talk about some of the case studies we've included, and then I'll be available for questions at the end. So over to you, Alec.
Hello, I'm Alec Tyson. I'm a mechanical engineer at Arup, and I was also a co-author on AM17. So yeah, within AM17, there's 5 case studies sort of littered throughout, and they're meant as sort of real world examples to help designers consider what system or configuration may work best for their project. The sort of typical format is they outline the initial design and then the benefits of the optimized design. And sort of the case studies within AM17 have been chosen specifically to highlight different aspects of the design process, and they're all from projects that are either sort of well on the way to being complete or complete installations. So within AM17, there are 5 case studies. The sort of case study, the first one is sort of a heat pump sizing based on an annual building load analysis, and that's for a sort of a large hotel in Scotland. Number 2 is sort of a ground source heat pump system, which is found sort of through monitoring that it was sort of varying from its design. That's a college building in Oxford. Case study 3 is sort of sizing of a cascade system on sort of building retrofit, and that's sort of a historic building as well. Case study number 4 sort of looks at buffer vessels as a thermal store. And case study number 5 is sort of source heat pump sizing based on sort of system volume and minimum turn down. So there's sort of a full spread of different case studies in the document. Oh,
sorry to interrupt. I'm just interrupting. Your sound has gone a little bit fuzzy. So I just thought before you carry on, we'll just check that just to make sure that the audio is good for the rest of the webinar. Oh no, seem to have lost you a bit. Do you want to try now?
Yeah, is that any better at all?
It's still making a little bit of an echo.
Sorry, is that any better at all?
Oh, that is much better.
Okay, great. Sorry. Yes.
Great. Sorry. Thank you, Alec.
No worries. Thanks. Can I get the next slide, please? Yeah. So I'll just go through three of the case studies. I've just sort of filtered down 3 to present today. So this is in no particular order. This is case study number 5. So it's an example of splitting one larger air source heat pump into 2 smaller units to improve the efficiency at part load. Doing so also had, in this instance, had the added benefit of removing the thermal store and therefore its sort of associated losses from the system. So in this case study, operating a sort of large air to water heat pump at part load for most of the year was not the most efficient solution. you can still see in figure 39 in the top one there, a thermal store was required in this situation because of the sort of frequency of cycling. However, in this particular example, splitting that out into a number of smaller air source heat pumps was considered to be better suited. It meant less cycling and a smaller minimum water content. The initial concerns with doing so were sort of capital costs, so they were expected to be slightly higher, and you'd require more plant space as well. However, sort of once the sort of design had been optimized, it sort of used two smaller sort of modular air source heat pumps at 50% duty, which sort of maximized efficiency at part load. And in actual fact, sort of the plant space actually ended up being similar to a single air source heat pump. And in this instance, as I said, you could remove the thermal store and the associated heat losses with that part of the system. And then from a sort of cost perspective, the optimized system paid back the increased capital costs in sort of, or is expected to within sort of 3 to 5 years. So a lot of the initial concerns with splitting it down were sort of addressed. And this is a good example of where removing thermal storage offers a system optimization. However, we highlight other situations in AM17 where thermal storage is required and perhaps even sort of beneficial as well. So the next case study I'll go through is an example of a retrofit project for a 112-year-old chapel in Cheltenham, where the emitters within the building couldn't be replaced, and they didn't allow for a low temperature system. So because they couldn't be replaced, a low temperature heat pump would be sort of unable to meet the demand for the building. There was sort of limited space for air source heat pumps as well to be installed on the outside. And through the sort of thermal modelling, it was found that a flow temperature of 68 degrees was required. So in order to achieve the sort of higher flow temperature, a cascade system was proposed. This is comprised of a low temperature air source heat pump and a high temperature water source heat pump in a cascade arrangement. The air source heat pump would sort of operate at 25 degrees flow and 20 return. And then the water source heat pump would operate at 68 degrees flow and 58 degrees return. And it was sort of found that this system had a sort of comparable efficiency to a single high temperature air source heat pump, but as it uses sort of a different refrigerant, so it uses R1234ZE rather than R407C, there was a 99.7% saving in the global warming potential of the system. And then by accounting for the contribution of the water source heat pump in the installed capacity, the air source heat pump size was reduced, so it was sized at 75% of the building load. And this approach sort of reduced the cost, embodied carbon, and also helped with the sort of limited space for positioning the air source heat pump. Having a smaller unit outside sort of made it a lot easier to install. And the final case study I'll go through is an example of sort of a ground source heat pump system that was installed at a college in Oxford. So the image on the screen shows annual ground temperature sort of monitoring throughout the year. And what you can see is a rise in temperature of 2 degrees sort of in the ground. The key issue sort of with a thermal power system, it's designed to have a balance between heating and cooling. This particular system was in balance throughout the year, and this is a sort of a key issue that impacts on the long-term performance and sustainability of a ground source heat pump system. It really needs to sort of be utilised as designed, and that balance needs to be maintained. This problem can be overcome by monitoring the installed system and reviewing the annual performance. This obviously allows for issues to be detected and resolved quickly. In this example, the thermal power system had a much higher cooling load being delivered than was designed, and this imbalance throughout the year led to a 2 degree rise in the ground temp as a result of overcooling. As a result of the monitoring, so because they were keeping an eye on it, you could sort of the error in the BMS controls was identified. The problem was resolved, ensuring that the ground temperature was not increased throughout the year. Yeah, that's the that's the end of my sort of case studies, and that concludes our author team presentation. I'm sort of going to hand back to Lucy now to sort of start the Q&A. But yeah, thanks very much for listening.
Great, thank you so much, everyone. Yeah, so just as a reminder, there is a question function on your dashboard, so please do feel free to keep submitting questions. We've got around 30 minutes now, so we can make our way through quite a few in that time. We also, just to let everyone on the webinar know, that you will receive a link to the recording of the webinar, including the slides. So without further ado, we'll launch into the first question that came up. So this is from Charlotte. At the early design stage, how do you start to define the load profile? Don't know who wants to take that.
I'll have a go at that. Yeah, so that's a really good question, because obviously at an early design stage, you've got limited time or budget to kind of do a really detailed annual model. The way that I've seen it done is you can start by looking, it also depends whether you're looking at a retrofit or a new build project. So ideally, if you've got existing data or data sources from similar projects, then that can be a really good source to start looking at. Otherwise, I would start by looking at, as you would do for any project, start looking at the what the peak loads would be and what are the different, so identify what the loads are, identify if there are any constraints on what temperatures for distribution or that you might have, depending on whether it's retrofit or whether you need particular emitters to be used for the application. And then if there are any client resilience requirements. And then in terms of looking at kind of daily, seasonal and annual profiles, it might be a matter of using existing data, using benchmark profiles, using a degree day methodology, creating a really simple simulation. There's a lot of ways you could make the process quite quick and simple that you can then fill in more detail later on. But obviously it does seem like a bit more work up front than might have been used on previous projects. But I can't really overemphasize the importance of understanding those annual variations as well.
Great, thank you, Iona. Just checking, Mike and Alec don't have anything to add.
I think the only thing I'd add to that, Lucy, I think I agree with what Iona said there, is just that as designers, as you get more used to designing and delivering heat pumps, the kind of historical past project experience you gain from doing that allows you to reapply that to your new project. So I think, yes, it's correct. At an early stage, you don't often have the time to do a lot of detailed simulation and analysis. But I think as we do more of this, then that will be fed back into the design process to really sort of assist you with that. Hopefully, some of the case studies we've got in AM17 also provide some sort of pointers to the kind of things you might do.
Great, thanks, Mike. So next question is from Elizabeth. Is the refrigerant choice key for reducing or limiting whole life carbon?
I'll take that one. Yeah. Yes, it is. It definitely is. So I think in Alex's example, he talked about changing. One of the examples he talked about how you might change from one size unit to other size units and how you might balance that with thermal storage. A lot of the work we're doing in assessing real project applications is to look at those loads and to really challenge ourselves around the size of the heat pump we've got, the numbers of heat pumps we've got, and the types of refrigerants that we've got. If you're working inside the GLA area where you've got to do whole life carbon assessments, in March they recently introduced new requirements where as part of your planning application you have to do whole life carbon assessments and you have to use Cibse TM65 methods to do that. So we are seeing lots of situations where what we thought might be a good solution with heat pumps, we're revising those when we've done a whole life carbon analysis, looking at the materials within the heat pump itself, but also the refrigerant you use. So there is a section of refrigerants covering GWP, but also covering things around safety and handling of refrigerant. So yeah, it's a super important issue. I don't know if you want to add anything, Alec or Iona.
I would just say that yeah, it's the choice of refrigerant is really important because the GWP can really vary enormously between different refrigerants. But it's not just the choice of refrigerant; it's how much refrigerant you have in your project. So how can you reduce the installed capacity, whether that's distributed to heat pumps or a central system? How can you make it smaller by using thermal storage or another, or like reducing your loads or being clever with the way that you control your system. Yeah.
Great, thank you. And the next one is from Dan. And he said he finds it difficult that different manufacturers publish acoustic data to different standards. Did AM17 look at this at all, especially, he says, for the ease of design, as if all data was standardized?
That's a really good question, actually, and something that I've personally seen as a struggle on multiple projects, because acoustics can be a really big consideration for heat pump projects, especially where you have air source heat pumps outside that might be near particularly sensitive developments or residential areas. In terms of the data and the standards that it's produced to, so I think our data sheet decode helps a bit with that and looks at kind of what you should be looking for or asking your manufacturers for. And we also look a bit about how you would design to reduce the acoustic impact of particularly air source heat pumps, and like how you should locate attenuators, plant screening, and that kind of thing. I think it's worth noting that with heat pumps, not just acoustically, but also from looking at efficiencies, it's really important to have an open dialogue with a variety of manufacturers and be really clear about what information you want against what standards. Because sometimes a generic data sheet won't give you, as you say, a comparable piece of information compared to another manufacturer. And so you just have to really sometimes ask for what you want. And I guess eventually that will drive the industry towards providing what we as designers want to see.
Great, thank you. Alec, I think this one is directed at you regarding the case studies. The question was, in the case studies, this is from Adam, how often was a utility upgrade required for a larger electrical supply to an existing building? And if you know that information.
I'm not sure I've got a great answer for that one.
Yeah, I think it's difficult because some of our case studies, they've come from a variety of sources, and we've really focused on how each case study is used to define a particular aspect of design. And I don't think we have any specific ones looking at electricity upgrade. It's a really good question though, because it's a really big impact of heat pump installations. But yeah, unfortunately, I don't have a good answer to that either.
Great, thank you. And another question, do any of you are able to answer what are the benefits or issues of an open loop ground source heat pump versus a closed loop one?
I'm happy to talk about that. I've worked on a few different projects where we've considered open loop systems versus closed loop systems. We go into quite a bit of detail in the document about this. I guess there's a few high level things I would say to consider, like an open loop system often requires a more significant upfront cost. You have your and quite a significant planning or engagement with the environmental authority, because you're looking at actually extracting water, groundwater, extracting heat, and then re-injecting that water. And so you've got a kind of you've got to look at how you're hydraulically affecting and thermally affecting the temperature and water movement within the ground, and so in the aquifer. So that has quite a lot of hoops you have to jump through with the environmental authority, and how it might affect neighbouring developments also trying to impose that system. Comparatively, a closed loop system, whether you're looking at thermal piles, so where the pipework's in the structural foundations of the building, or a vertical or horizontal collector in the ground, that requires, because it's just a closed circulating fluid, that can be quite comparatively cheaper and less difficult to implement from a planning perspective. However, the benefit of an open loop system is that you're a little bit less tied to having an extremely balanced heating and cooling load, and you can get quite high efficiencies. With a closed loop system, you really are much more tied to having a balanced heating and cooling load. There's some of the key things, but there are yeah, we go into it in quite a bit of detail. I don't know if Mike or Alec want to add anything.
I think the cost issue is very important, and it's something we come up against in a lot of projects, particularly with open loop systems where it requires some significant well drilling. It also requires quite a lot of sort of geological survey at an early stage, and you've got to understand a lot about the groundwater flows. And often, you know, the cost consultant will need to allow for a number of wells to fail to give us the sort of resilience that we'll actually be able to get a working well at the end of the project. So that can really add up at an early stage, and it often means that they become unviable from the client's perspective. So yeah, but I mean, I think the issue of balance, you know, Alec's case study highlighted what happens if you don't control a closed loop system well throughout the year, you don't monitor it, and it becomes imbalanced and it works inefficiently. So you know, there are pros and cons to both, and I think it's really a question of looking at your site and understanding the ground conditions at an early stage to determine which of those might be most feasible. But you know, making the client aware of the risks is really important, and working closely with the cost consultant, because you know these things are going to be very much at the forefront of people's decision-making process.
Great, thank you. Next question here. Have you found any data or statistics on the leakage or loss rate of refrigerants in different types of heat pumps? I think they've kind of given a bit of an example, e.g. different compressor technologies, noting that this has a large impact on life cycle greenhouse gas emissions.
It's a good question. It's something that I think we highlight a bit in the datasheet decode. But again, it's really, you know, there are certain sustainability targets for different accreditation schemes and different planning requirements and different targets for what that leakage rate should be. And you're right in saying that depending on the GWP, it really affects your whole life carbon. In terms of which technologies have better leakage characteristics, I can't really comment on that. I think the technology keeps changing, and it's going to be not just technology specific, but manufacturer specific, what kind of installation you have. There are a lot of different factors that could affect that leakage rate, but it's something that we need to design for carefully.
Yeah, I think it's a really good thing to be challenging manufacturers on. Not to say manufacturers are not thinking about this, but you know, in terms of the information you want to know for your whole life carbon assessments, that's something that they need to be getting a clear idea of how to provide you that information so you can make good decisions.
Great, thank you. And this is another one from Jordan, asking about the content of the AM17. Does the AM refer to VRF heat pumps where the refrigerant loop employs direct refrigerant expansion directly into the heating buffer vessels? I think just wants a little bit more information around that, and if that has been included.
Yeah, we have a section on VRF and DX systems within the document. I don't think it specifically covers inputting into a thermal store, but obviously, as Ian has talked about, we cover thermal storage design in some detail and other aspects of hydraulic design. So yeah, we discussed this at length with the steering group, and the peer review is around what should be covered, and that's within the document.
Great, thank you. And another one, AM17 focuses on loads of 45 kilowatts and above. Is there a recommendation for below that for similar building types, or is there a thought that this is suited to a more domestic type approach?
So I think we thought about this when we were kind of defining the scope of the document, and you know, but I would say, although this has been written addressing non-domestic developments above 45 kilowatts of thermal load, the approach would be very similar for if you read AM16, which was a domestic, again, that was for multi-unit domestic buildings, but the approach for designing a heat pump system and the considerations you need to make are still very much the same. It's what are the loads? What technology are you going to use? How are you going to size that? How are you going to operate it efficiently? There are obviously like more off-the-shelf solutions that you might be considering if you're just looking at an individual home. And we haven't really considered those in as much detail. We've been looking at larger systems, but I would say, yeah, the approach and the considerations are still exactly the same for any size installation.
Great. Luke has said, as this is a newer document, is there any general information in AM17 that is still relevant in AM16, or has that already been covered in AM16?
Yeah, well, this was an interesting question, Luke. We definitely needed to make sure that we weren't covering completely the same ground, but obviously there are some common themes where information from AM16 is also relevant here. So we do sort of, there certainly doesn't supersede it. It's a different application, so it's really about the type of building you're looking to design for. But you may find that there is some information here and some information in AM16 which can be used together to give you a better result. And a lot of our projects are mixed-use developments where you're looking at large residential units alongside commercial and other types of uses. So I think you find a lot of good information in both. But it is a document that stands on its own 2 feet. It has the same sort of introductory sections and the same sort of guidance that I talked about earlier on about how to use the guide and how to navigate your way through it. So yeah, they don't need to be read together.
Great. And this one is referring to case study 5. So based on case study 5, do you derive to the conclusion that modular heat pumps is a valid solution to either replacing or new projects for both efficiency, water volume requirements, etc.? And that comes from Christopher's.
Sure. I think in that particular example, it was the right solution. But I mean, as sort of mentioned, the case studies, obviously they're very specific to the to the project they're working on. So I think in that case it was a great idea, but there are other considerations that need to be made.
Yeah, I think we just echoing what Alex said. We don't want the case studies to represent the solution for that particular type of building or that situation. Iona's made the point that, you know, getting into the loads and looking at the sort of seasonal loads, part loads, the general requirements of the building is the key thing here. The case studies illustrate in that circumstance that that's the case, but you might find a different result if you have a different specific load requirement. So, but yeah, modular heat pump solutions can be very powerful.
Great. There's also a question here regarding heat pumps and the kind of energy strategy. So how should people overcome the kind of conflict between requirements for heat pumps to match the energy strategy and requirements from district heating, which they required completely different flow and return temperature to those of the heat pump operates?
I guess that's a good question. I'm not sure I completely understand it, but I think perhaps what they're referring to is the requirement at planning to have a connection to a district heating network, or to show the potential for a connection to a district heating network, particularly part of the London plan, and how the temperatures for that future district heating or cooling network might contradict heat pump temperatures for the installed heat pump system. I think distribution temperatures are a really important consideration, both when you're moving from retrofitting a heat pump system and comparing how your system that you're designing now might be future-proofed against a future district heating system. It's worth noting that future district heating systems might well be using centralized heat pumps or an ambient loop situation to provide that district heating. So I don't think they're necessarily at odds with one another. And it's worth, but yeah, I think future proofing is really important. So you just need to think about what the potential temperatures might be, and how over the life of that development, what the appropriate distribution temperature range and pipe sizing and everything should be from a whole life carbon perspective for that development's life.
Great, thank you, Iona. Question here about the content. How is refrigerant leakage managed within the document from a guidance position?
So I think we touch upon it in the kind of policy section, and also in the operation and installation sections. And yeah, I mean, I think we look at what the legislation requires, and how you might do best practice design. I think we kind of discussed this a bit with the previous question about, you know, what might be the best technologies for leakage, and again, you know, speaking to manufacturers and working out the best way to prevent leakage for your specific heat pump installation. But yeah, it is something that's important and which we've highlighted in the document.
Yeah, we also talk about that within the plant space allocation section around leak detection in plant room requirements. You know, the thresholds that one of the BSs outlines, and you know, how that has implications on sort of frequency of testing. We also touch on sort of BREEAM credit requirements for leak detection. So yeah, we have covered that to some extent.
Great, thank you. A few people have asked questions regarding listed building, and someone's asked if you could comment on dealing with heat pumps in listed building applications and what other considerations are required, and perhaps whether that's touched on in the AM.
Well, yeah, listed buildings are tricky when it comes to retrofit generally, not just for heat pumps. I mean, I think that a lot of the discussions we have early on are around identifying your load profiles, and you know, attempting to for good sort of energy efficiency and sustainability reasons to reduce your loads. That can be challenging with listed buildings where you cannot make major modifications to the envelope, to the facade, to the glazing. So we touch on some of the sort of solutions around that, but we don't focus on listed buildings specifically. More in the case of, you know, existing buildings about reducing loads. I think my main comment on that would be that there are opportunities with listed buildings to do sensitive renovations, to do sensitive replacement of glazing, to do internal insulation, to look at other ways to reduce loads. And there are newer technologies coming to market that allow kind of higher temperature outputs from air source heat pumps, which might better suit buildings with where it's more difficult to reduce the loads. So I definitely want to encourage people not to rule out installing a heat pump in a listed building. I think heat pumps can deliver heat in most buildings. It's just going to be a case of how effective and efficient and easy to do that is. Obviously, it's much more efficient and cost effective if you can reduce the loads first.
Great. Just check Alec and Iona. Just check you don't want to add anything. Great. So this next one, does AM17 give guidance on the performance gap between typical designs and actual building demands? It's from Darren.
That's a great question. Yeah, I think that's something that we've really seen as something, yeah, it's really important, and kind of part of the reason that I've emphasized, you know, understanding your loads, because I guess if anyone listening doesn't know about the performance gap, it's kind of describing the difference between how we expect our heat pumps or any building to operate in terms of energy efficiency, and how we actually see them operate. And we talk about modeling techniques and how you can accurately you know, do annual building simulations and really try and capture the control system for your building and in your modeling, and try and make sure that it's representing realistic situations. And when we look at deciding what you're like, trying to understand your loads, again, that's why it's not just important to look at what's the maximum peak load in a very isolated situation when it's really cold outside and there's no one in the building. It's about what are the actual situations that the heat pump system is going to need to deal with on an annual basis, and how do those loads vary, and trying to get that as accurate as possible, because that will really determine how the building operates. And again, I think when I was talking earlier about the control strategy, and the person who's designing the system needs to understand like, how do you want the system to operate? So how are we going to stage the heat pumps? How are you going to charge and discharge the thermal store? It's not enough to just specify the equipment and walk away. So we talk about it from a modeling and best practice perspective as well. I don't know if Mike, you want to add anything there?
I agree with all that. It's a great question, and the other element that I'd refer back to is the datasheet decode part, where getting that information from manufacturers and understanding what they're telling you and what you can do with that, and what other questions you might need to ask to follow up to understand that part load efficiency is going to be critical, because heat pumps don't work at standardized lab test conditions very often. So it's really important to understand the sort of the full working efficiency across a range of external source temperatures and loads as well. So yeah, the performance gap. When I talked at the start about delivering successful applications and not losing confidence in what we're delivering, that's a really important thing to think about, and hopefully the guidance we're providing will help a bit with that.
Great, thank you. We're just kind of coming to a close now. So I just wanted to kind of go down the panel now and just see if you've got any final things that you want to say regarding the AM17 release. Perhaps if you share what you think is one of the greatest takeaways from the AM. Iona, perhaps we start with you.
Yeah, I think, yeah, I'm excited that people have a freely available, sorry, I think I can just hear myself echoing.
Oh, yes, echo.
Yeah, no, I'm excited that it's freely available, and that I'm excited that perhaps this will give people the opportunity to understand some of the, I guess, I've seen designers challenged by the increasing use of heat pumps, and I'm hoping that this document kind of addresses some of those challenges. And I guess the thing that I'm interested in is seeing how we move from using heat pumps just to address operational carbon, but how we can consider them from a whole life perspective, and kind of using TM65 and driving manufacturers towards considering, yeah, the embodied carbon impact of their systems as well.
Great, thank you. And Mike?
Yeah, I think if you think about the scale of delivery of heat pumps over the next few years that's anticipated and required, I just think it's really important that this is considered very carefully and it's delivered well. So I guess I'd hope that people would use this guide to support their work in making that happen. All of the people listening are probably involved in, I'm assuming that's why you're here, in designing and delivering heat pump installations. So we all need to work together to make this really successful, and hopefully this is a kind of a kickstart for that, and making sure that people do know the complexities of this, and they're not just assuming you just plug in a 500 kilowatt heat pump and off you go. There's more to it than that, but working together we can make it work really well. I'm very confident and optimistic about that.
Great, thanks, Mike. And Alec, final words?
Yeah, sure. So I'm obviously still a relatively junior engineer, and I think that the thing that probably excites me the most about AM17 is it's a really good guide for someone at my stage, at the same stage as me in my career as well. So we sort of peer reviewed it with people that are similar age to myself, and they all found the same. It's just it's a really useful guide, and it'll definitely help a lot in the design process.
Great, thank you. So I just want to say thank you again so much to our panel, Iona, Mike and Alec, for today. For everyone listening, you'll receive an email tomorrow morning with your certificate of attendance and with a link to the webinar recording and the slides. Also, as Iona touched on, it's been very important that this AM17 can reach as many people as possible. And so it is free to download. You just simply need to use the code AM17 at checkout, and that will be included in the email tomorrow. So thank you very much for joining, and we hope you'll join us for another Grow Your Knowledge webinar soon. Thank you very much.
Thank you all.